Now we are ready to formulate Lagrangian mechanics. It's formulated using principle of stationary action. This principle has a name. It's called Hamilton's principle. It shouldn't be confused with the Hamiltonian formulation of mechanics. The main role in this principle plays action, which is a functional defined using independent variable time, function Lagrangian, which is itself a function of coordinates, which we will denote as q, and velocities, which we will denote as q dot. Action has units of energy times time. Q's are generalized coordinates. These generalized coordinates don't need to have units of length. For example, it could be angles and so forth. So our notation for the set of Q represents n variables that specify coordinates or specify position. This combination of all of the coordinates is known as configuration space. So likewise, our notation of generalized velocities, as you can see, dot denotes full derivative with respect to time. These are generalized velocities. So what is Lagrangian? Lagrangian is defined as kinetic energy minus potential energy. So the principle of stationary action states that the motion obeys equations such that the action is stationary. In other words, it means that the functional derivatives with respect to positions q1 and so forth are zero. As we know, this requirement gives rise to early Lagrange equations, which in mechanics are simply known as Lagrange's equations. Let's write them. Partial derivative of Lagrangian with respect to coordinate q sub I minus full time derivative of partial derivative of Lagrangian with respect to velocity of q sub I equals 0, and this is for I equal 1, 2, all the way to n. So these are Lagrange's equations, which are equations of motion. We can add a few words by saying that Lagrangian is postulated. So we don't need to derive it, and what it means is that it's true because equations that it produces are true. Let's add also a remark about when Lagrangian mechanics can be applied. So for this we need some terminology, some additional terminology. So degrees of freedom is defined as number of independent directions to describe all positions. So to describe all positions and describe the system uniquely. For example, if we have n particles in 3 dimensions and we have k constraints, then degrees of freedom will be given by this equation. Once again, this here is number of particles. Factor of 3 designates the fact that we work in 3-dimensional space, and k will be number of constraints. Now, that's what we would typically expect. If number of degrees of freedom is equal to the number of generalized coordinates n, where we defined this set as this collection of n generalized coordinates, then we have what is called holonomic system. Holonomic system. We will define this concept more rigorously later when we deal with constraints. Not all constraints are holonomic constraints. But if we have a system where the generalized coordinates that we have are in fact degrees of freedom that describe system fully, its configuration space fully, then Lagrangian mechanics applies. So, in other words, Lagrangian mechanics requires, there will be some additions later, so let's say so far, as we'll see, we can relax some of these requirements. It requires 2 things. First, that the system that we're dealing with is holonomic system. And second, that we are dealing with conservative forces. In other words, forces for which a derivative of potential energy gives the force. As we will see later, this particular requirement can be relaxed. So we have formulated Lagrangian mechanics. Once again, we have the principle of stationary action defined in terms of Lagrangian, which is itself given by kinetic energy minus potential energy of the system, and is written as a function of generalized coordinates and generalized velocities and time as independent variable. And the requirement of stationary action leads to Lagrange's equations, which are written here in terms of partial derivatives with respect to generalized coordinates and generalized velocities.